Okay, my calculus friends, here we are again with some, in this case, linear approximations. Okay, so we're going to write our equation in point slope form. Okay, point slope form, y minus y1 equals m times x minus x1. So there are three things that we need to know. Number one, what is the x value from your problem? Right, we're always going to have some type of an x value. And then we're going to have the slope, right? The slope of our line is found by finding the derivative and evaluating it at that point. And the third thing we need is the y value for your given x value. Okay, those are the three parts that we need to write any equation of any tangent line. And then we're going to use that tangent line to find an approximate y value just a little bit away from your given x value, right? That's why we are approximating. We're not going to use the formula directly. We're going to use this tangent line to approximate it. Okay, so here are basically your steps for our first problem, which is y equals x squared. Write an equation. Well, this is what you're going to be asked to find, right? This is what we're doing. We are finding the actual approximation for f of 1.01. That is what we are doing. Approximating the y value for f of 1.01. Okay, and then these other things are just to find some error, right? What is the difference between the actual value and our approximated value? For, once again, this function y equals x squared. Okay, so let's set this up real quick. Let me graph y equals x squared for us. Okay, it has a vertex at the origin. When x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is also 1. So we're going to have this parabola, this parabolic graph. Okay, we want to know what is the y value for 1.01. Right, so what is that y value? Right here, right? It's going to be something really close to positive 1, and we're going to use our tangent line, right, to approximate that. Okay, so that's basically what we are doing, finding the y value for a given x value, but not the exact. We're going to use an approximate. And of course, the closer that we actually get, the better the approximation is going to be. Okay, so that's the setup for what we're going to do. First, we need to figure out what is the equation of this tangent line that passes through the point 1, 0, or 1, 1. Okay, so the first thing we need is the y value, which is, let's see, if f of x is equal to x squared, then f of 1 is 1 squared, which is 1. Okay, that's pretty good. Right, we have the point 1, 1. I think we already talked about having the point 1, 1, but there we've calculated it. Now we need to find the slope. And the slope is found by taking the derivative. So if our function is x squared, the derivative is 2x. Right, it's the power rule. We bring the power to the front, subtract 1 from the power. So our derivative is 2x. So then what is the slope of our line when x equals 1? That's going to be positive 2. So we have calculated the two things that we need. Number one, the y value, and number two, the slope. So we can write part A, write the equation of the tangent line. Y minus 2 equals slope times x minus 1. So now that we have our linear equation, we're going to plug 1.01 in for our x value and do all the math to simplify this down to see what our y approximate value is going to be. 2 times 1.01 minus 1. Okay, well 1.01 minus 1, that's 0.01. And then 2 times 1.01, that's 0.02. And then if I add 1 to that, my y value is approximately 1.02. No calculator needed. Okay, so 1.02 is my approximate value for f of 1.01. Okay, so now let's actually get a calculator and see exactly what the calculator says the y value is at 1.01. So here is what my calculator says is the actual value for 1.01 squared. 1.0201, right? 4 decimal places. Well, I have 2 decimal places, so what is the error? The error is the actual value of 1.0201 minus my approximate value, which is 0.0001, right? 1/10,000th is my error. So in other words, that's pretty dang close for this approximation using our tangent line rather than my direct calculation using a calculator. Okay, so let's use that for this next example. Use a tangent line approximation to evaluate the third root of 127. Okay, to approximate, right? We're going to approximate it. So we're going to use this as our function, right? We're taking the cube root of something, so we're using the cube root function. And it says choose a perfect cube close to 127. So let's see, let's go through our cubes. So notice that 5 cubed is 125. 125 is pretty close to 127. So we're going to let x equals to 5 in order to write our equation of your tangent line. Okay, x equals 5. No, x equals 125. Sorry, that is not right. We're going to let x equals 125. X equals 125. That's what we're going to do. Right? Because if we want to find something close to 127, right, 5 is not close to 127. But 125 is close to 127. Okay, so if x is 125, then y is the cube root of 125, which is 5. Right? That's where the 5 comes in. 5 is the y value. Now the third thing we need to do is find the slope. And the slope is the derivative. So what is the derivative of x to the 1/3 power, right? That's what the cube root of x is, the 1/3 power, right? And we want to apply the power rule. That's probably the easiest way to do this. So the power rule says 1/3 of x to the negative 2/3 is going to be our derivative of x to the 1/3. Okay, so we can write this maybe in a form that's a little bit easier to understand. That's the cube root of x squared. 1 over 3 times the cube root of x squared. And what is our x value? Well, our x value is 125. So we've got to plug 125 into here. 1 over the cube, 3 times the cube root of 125 squared. Okay, now I don't know what 125 squared is, but I do know that if we take the cube root of x squared, that's the same as taking the cube root of x squared. Okay, that I can do, right? Because I know what the cube root of 125 is. The cube root of 125 is 5. I know what 5 squared is. That's 25. So 25 times 3 is 75. So that's the slope of my tangent line when x equals 5. 1 over 75. So the equation we're looking for, y minus 5, that's the y value, equals our slope, our derivative 1 over 75 times x minus, let's see, I didn't have a color, but 125 is the original x value that we chose up here. Would that x be 125? Okay, so that's the equation that we're going to use to approximate what happens when x is 127. Okay, so y minus 5 equals 1 over 75 times 127 minus 125. Okay, so this is the equation that we're going to use in order to figure out what that y value is, the cube root of 127.
Are you writing this on?
Okay, so this becomes
Are we still writing this
2 over 75. Right, I'm going to add 5 to both sides, plus 5. Okay, so if I want to really figure this out, I need to write 5 as something over 75. So let's see, 5 times 75 is, now that my denominators are the same, I can add these together to get 377 divided by 75. Right, and that's an exact value, so you can put that into your calculator to make it into a decimal. But that is what the cube root of 127 is approximately equal to that fraction, which is probably 5.000 something, pretty close to what it actually is going to be. So here's another way that we could do linear approximations. If we knew how far the distance in between your y values are going to be. Okay, so let's look at what it says. We're looking at this dy dx business, right? That's how we write the derivative of y with respect to x as this fraction. So let's use our equation here. dy is always the independent variable, and dx is the independent variable. Okay, so let's see. Find the differential dy given y equals, okay, so we're going to use that definition and take the derivative, which is dy dx equals, what's the derivative of 5x cubed? 15x squared. Okay, so we start this off just like you start off any other derivative, but now we're going to multiply both sides by this denominator to get our differential. Okay, dy equals 15x squared times dx. Okay, so dx is the difference between your two x values. Sometimes called delta x, right? The change in x. That's what dx stands for. It's the difference or the change in your x values. We started with an x value of 1, and we're looking for an x value of 1.01. Right? That was our first example. We had x equals 1, and we were approximating at x is x.01. So then what is our change in x? Well, that's just your 0.01, the difference between 1 and 1.01. So delta x, or dx, is the change in your x values. Okay, so it's different looking, but there's not really much difference in the mathematics here. Okay, so example, the radius of a circle increases from 10 to 10.1. So what is our delta x if we started at 10 and went to 10.1? 0.1, right? We had 1/10 of a change in the length of our radius. So dA is probably the area formula, right? So area equals pi r squared. Right? You need to memorize the area of a circle formula. It's never going to be given to you on an AP test. So memorize that one. So now let's take the derivative. This is dA over dr, because r is your other variable. It would be ridiculous to put an x in there. Equals 2 pi r, the derivative of pi r squared. Okay, now in order to make our differential, we're going to multiply both sides by delta r, right? The change in your radius. So the change in area equals 2 pi r times dr, the change in our radius. Okay. So 2 times pi, that's standard. What was our radius to begin with? To begin with, it was 10. So 10 goes in there for your radius. But what is your change in radius? 0.1. Okay. So the radius is what the original was. This is the original radius. And the delta r, or the dr, is your change in your radius. So let's see if we can do this without a calculator. This is 20 pi times 1/10. What's 1/10 of 20? 2. So 2 pi would be the increase, the estimated increase in the circle's area from changing it from a radius of 10 to a radius of 10.1. Okay, compare the estimate you found with the true change in area. So our area was pi r squared, so pi times 10 squared, which is 100 pi. Okay, and then our second area is pi times 10.1 squared, which is 102.1 pi meters squared. Okay, so from 100 to 102.1 pi, well, that's pretty much exactly 2 pi. So pretty close to the original, the approximation, right? And the closer your delta x is, the smaller your delta x, the better the approximation is going to be. Okay, so remember, delta x is the change in your x value, the change of your independent variable. In this case, the independent variable is the radius that we're doing.